This is B. Naresh, working as assistant professor in ICA department. And today's topic is the question bank discussion on transistor biasing and stabilization. So, in this session, we are going to discuss some of the problems and the questions related to the transistor biasing and stabilization module. So, the first question is, in a silicon transistor circuit with a fixed bias, VCC is 9 volts and collector resistance is 3 kilo ohms. RP means the base resistance is 800 kilo ohms, beta is 50, and the base to emitter potential difference between base to emitter, that is VB, is 0.7 volts. Solve the operating point and stability factor. So this is the given circuit for the fixed bias. So means here we consider as a common emitter configuration, and we use the NPN transistor. And the biasing method is a fixed biasing method, means the base resistance is biased with a constant DC voltage source, that is VCC, and here the VCC value is 9 volts, and the collector resistance they are defined as 3 kilo ohms, and the base resistance is 800 kilo ohms. And for this transistor, the DC current gain is represented as 50, and the potential difference between this base node and emitter node, that is represented as 0.7, means when emitter base junction is a forward bias, and this particular junction is acts as a conducting state, hence the voltage drop across this conducting state is represented as 0.7 volts. For this case, we need to find out the operating point, means the Q point is the functioning of the output current, that is collector current, and the output voltage is VCE. And we need to find out the stability factor, that is also S in this fixed bias. So let us, and if you want to find out this IC, means we know that IC is equal to beta times of IB plus 1 plus beta times of ICNR. If the reverse saturation current is a very small compared with your input current, then IC is approximately equal to beta times of IB. So first you should determine this base current from the given circuit. So if you observe, means we need to find the base current from this input node, means VCC node to this node, and here then this node is contains the potential remains VCC, and another node contains VB, means I is nothing but V by R, so means the voltage drop across this resistance, that is RB. So hence the IB is represented as VCC minus VB by R. Now again substitute the VCC value, they given that 9, and the VB value is 0.3, and RB is 800 kilo ohms, means. So based on that, then we can observe this IB value is 10 microamperes. Now we need to calculate this IC. So how to identify this IC? IC is represented as beta times of IB, hence now can substitute the beta values are given, specifications are 50, and IB is 10 microamperes, means 10 into 10 to the power of minus 6. Then it becomes the collector current is so this is means 500 into 10 to the power of minus 6. So hence that is 0.5 milliamperes. So the collector current is now 0.5 milliamperes. Then to satisfy the Q point is a functioning of IC as well as VCE parameter. So hence we should calculate now the VCE parameter. To identify this VCE parameter, then we need to apply the KVL as the output to for a given circuit. Let us say if it is a circuit, then apply the KVL analysis at this output side. And from this, if you write the KVL equation, so how to write this one? The node is VCC node, that is equal to the voltage drop across this RC is represented as IC times RC plus the potential difference between this collector node and the emitter node is represented as VC. So hence from this we can write this VC is equal to VCC minus IC times of RC. So hence now we are going to calculate the Vce parameter. So hence from that the Vc is represented from the circuit at the output side based on the KVL analysis. The Vc is represented as VCC minus IC times of RC. Now hence actual VCC is a 9. IC just now we got the 0.5 milliamperes and RC is 3 kilo ohms. So hence it is 3 into 10 power 3. So this 10 power 3 and so then it becomes 9 minus 1.5. So hence it is 7.5 volts. So hence VCE is 7.5 volts. Means the ICQ, we need to define the Q point. ICQ is 0.5 milliamperes and the VCEQ is 7.5 volts. So this is the operating point for a given specifications of the fixed bias transistor. Now we need to calculate the stability factor. So we know that the stability factor in a fixed bias is represented as 1 plus beta. So hence the beta is defined as 50. Hence the stability is 51. The stability factor is 51. Now see another question. In a silicon transistor circuit with a fixed bias, VCC is 12 volts, RC is a collector resistance is 330 ohms, and IB is 0.3 milliamperes, beta is 100, VB is 0.7 volts, and solve the value of bias resistor RB and stability factor. So for this case, now means let first you draw this to attempt this one. First you should draw the circuit. So then we are going to use a silicon transistor with a fixed bias. So let us consider a common emitter configuration, and a collector is a bias with a resistance, that is collector resistance. In the specifications they given that RC is 330 ohms and it is a bias with a DC source, that is plus VCC. So VCC is 12 volts. Then we are going to use the fixed bias, means a base resistance is a bias from the DC source to base, and here it is represented as RB. Then it allows a base current, that base current is 0.3 milliamperes. Now for this base we are going to apply the Vn, and emitter is connected to ground potential, and at this point the potential difference is 0. Means that is nothing but a VBE on. So that VBE on is a 0.7 volts. Let us take this is collector and emitter, and this is the base. So then from this, now we need to calculate how much base resistance is required and how much stability factor is offered by using this circuit. So for this case, the transistor DC current gain is represented as 100. So beta value is 100. Now to identify this base resistance, now apply the KVL analysis at the input side. So from this, how to write this KVL analysis, we know that. So if you want to write the base current I is equal to V by R, from this I'm going to write. So from this I is equal to, means I means the base current, IB is equal to, the V means the potential difference between this node and this node, that is VCC minus VBE by the resistance is RB. So from this what we require, we need to calculate the base resistance, how much base resistance is offered. So from this mathematical relation, you should rewrite this equation in terms of RB. So from this, RB is equal to VCC minus VBE by RB. So VCC minus VBE by I. So here can the known parameters. VCC is the known parameter, that is 12 volts. VB is a known parameter, that is 0.7, and IB value. So what is IB value? IB value is 0.3 milliamps. So means this is 0.3 into 10 to the power of minus 3. So means this is 11.3 divided by 0.3 into 10 to the power of minus 3. Then again this ratio gives that RB value. Now then another question, another factor we need to determine, that is stability factor. So S we need to find out. So based on the biasing configuration, in a fixed bias, we know that S is equal to 1 plus beta. So for this fixed bias transistor, the beta is defined with 100, hence 1 plus 100, that is equal to 101. This is the stability factor for this given specifications. Now, another question. An NPN transistor, if beta is 100, is used in common emitter circuit with a VCC is 10 volts and RC is 2 kilo ohms. The bias is obtained by connecting 100 kilo ohms resistor from collector to base. Find the quotient point and stability factor. So means they are using the collector to base resistance. So and they are using the NPN transistor, and for this DC current again is represented as 100, and the VCC, the DC biasing voltage, is represented 10 volts, and the collector resistance is represented as 2 kilo ohms. Then the bias is obtained by connecting 100 kilo ohms resistor from the collector to base. So hence that is the reason this biasing resistance. So this biasing resistance is from this node to this node. We place the a biasing resistance, that is RB. So here this RB value is 100 kilo ohms. Is connected from the collector to base. Hence the biasing is called as the collector to base biasing method. So by using this collector to base biasing method, we need to find out the operating point or a quotient point as well as the stability factor related to this biasing method. So whatever the biasing methods, the operating point or quotient point is a functioning of output current. That is, in this case, there is in the C configuration. Hence, the output current is a collector current, and the output voltage, that is collector to emitter voltage, that is VC. So hence, first we need to determine IC and the VCE parameter. These two defines the quotient point or a Q point. So hence, from the given specifications, beta is 100, VC is 10 volts, collector resistance is 2 kilo ohms, RB is 200 kilo ohms. Now we need to find out first to identify this IC. We know that generally IC is represented as beta times of IB. So that is the reason. First we need to determine how much base current is flows with respect to the biasing parameters, that is biasing voltage and biasing resistances. So if you observe this, means if you apply the KVL analysis from the VCC node to input node, and from this I'm going to calculate this IB. So means how to write this one, VCC, so minus, and the voltage drop across this one is IC plus IB times of RC plus, and again IB current flows across this means IB times of RB plus VB, that is equal to 0. So by using this relation, now we can simplify this IB. IB is equal to VCC minus VB minus IC times of RC by RC plus RB. Now again, so now I simplify this one, that is equal to, so just I cross multiply this one, and from this, so if we derive, now we need to derive the IB in terms of the known parameters. If you observe this relation, here IC is unknown parameter, that is the reason. This mathematical relation we are going to convert into the known parameters here. So hence, now I am going to substitute this IC is equal to beta times of IB. So why? Because of the beta is a known parameter. Only the unknown parameter is only the base current. So hence, I'm going to convert these two unknown parameters to only one unknown parameter, that is IB. Hence, from that, IB is represented as VCC minus VBE by RC plus RB plus beta times of RC. So here are all the known parameters. So hence you can substitute. So what is the VC value here? So here I'm going to substitute. What is the VCC value? VCC is a 10, VBE is a 0.7, and RC value is a 2 kilo ohms, 2 into 10 power 3, plus RB value is 100 kilo ohms, 100 into 10 power 3, plus beta value is 100, and again RC value is 2 kilo ohms. Then you can simplify this one. It gives the base current is, so then you can simplify this one. It gives a base current. So this is nothing but this factor gives a base current. Now this IB, now we need to determine the collector current IC. So what is the collector current? IC is equal to beta times of IB. Here, so here the beta is 100. Now you can substitute this IB value here to get this IB. Then after that, we need to calculate to satisfy the Q point, we need to find out the VCE. To observe this VCE, apply the KVL at output side, then write on the loop equation. So hence VCC is equal to IC plus IB times of RC plus again the output potential difference is VC. So from that, I'm going to write this VCE parameter. So hence the VCE is equal to VCC minus IC plus IB times of RC. So now we can substitute these values. So VCC is a 10 volts minus. So in a previous case, we observed this IC value and IB values. Now we can substitute this in this relation. Substitute this VCC value and substitute IC value and IB value. RC is that is a known parameter 2 kilo ohms. Then to observe this, how much VC is produces here. So here this is beta is 50. So here the beta is 100. So we are not observe this IB and IC. Just you can find out the IB values and IC values based on the given specifications. Then we need to find out the stability factor. So for this a collector to base bias, the stability factor is defined as 1 plus beta by 1 plus beta times of RC by RC plus RB. So now we can substitute 1 plus beta value is 100 divided by 1 plus 100 into RC value is 2 kilo ohms by RC again 2 kilo ohms plus RB value is 100 kilo ohms. Now we can solve this one. It gives the stability factor. Then another problem, which looks like what we discussed the previous problem. An NPN transistor, if a beta is a 50, is in a common empty circuit. VCC is a 10 volts and RC is a 2 kilo ohms, and the bias is obtained by connecting 100 kilo ohms resistor from the collector to base. Then find the quotient point and stability factor. So it also looks like what we discussed the previous problem, but the beta value for this case, the beta is defined as a 50. So then we need to find out the same IC values and VCE parameter and the stability factor. To identify this IC parameter, then IC is equal to beta times of IB. So hence first we need to find out the IB value. So from this, the IB value is, we know that just use this mathematical relation. IB is equal to VCC minus VBE by RC plus RB plus beta times of RC. So then you can substitute these values. VCC is 10 minus 0.7 divided by 2 into 10 power 3 plus RB is 100 into 10 power 3 plus beta is 50 and RC is 2 into 10 power 3. Then you can solve this one. It gives that IB is equal to 46 microamperes. Similar to that, we identify that the collector current IC. So we know that from the generalized expression, IC is represented as beta times of IB. So hence this is 50 into IB value is 46 microamperes, hence 46 into 10 to the power of minus 6. It gives that IC is 2.3 milliamperes. So now we need to calculate the stability factor for this. And before that, first we need to find out the Q point. To observe this Q point, then apply the KVL analysis at the output side again. From this, we should derive this relation. Vc is equal to Vcc minus IC plus IB times of RC. Here Vcc is a 10 minus IC value is a 2.3 milliamperes and IB value is 46 microamperes into RC value is 2 into 10 to the power of 3, 2 kilo ohms. Then you can solve this one. It gives that VCE value is 5.308 volts. Hence, the Q point is ICQ and VCEQ. So what is ICQ? IC value we observed that 2.3 milliamperes. Hence, this is 2.3 into 10 power minus 3. VCEQ is 5.308 volts. Now we need to calculate the stability factor for collector to base bias. So hence this is S is equal to 1 plus beta by 1 plus beta times of RC by RC plus RP. Now this is 1 plus 50 by 1 plus 50 times of RC value is 2 kilo ohms by RC plus RP. Now it gives the stability factor, that is 25.75. Let's see another problem. Determine the input impedance, output impedance, voltage gain and current gain of the CE amplifier using H parameter model for the transistor. They given that input impedance means H parameters like HIE is 3.2 kilo ohms, HFE is 100 at the operating condition. The specifications for the voltage divided bias means to design the CE amplifier we are using the voltage divided bias. And for this network, it contains the specifications like R1 value means the resistor 1 resistor value is 40 kilo ohms, R2 is 4.7 kilo ohms, and the collector resistance 4 kilo ohms, and emitter resistance is 1.2 kilo ohms, VCC is 60 volts. For these given specifications, we need to use H parameter model. Then we need to identify the input impedance, output impedance, voltage gain, and current gain. To understand this one, just you can recall this CE amplifier using the small signal model analysis video session. And there we observed the parameter, how to calculate this input impedances and output impedances and voltage gain and current gain. So you just directly I'm giving the formulas, mathematical relations for the given specifications. So from the H parameters, we know that the input impedance Zi is the parallel combination of base resistance and HIE. So means first we need to find out this RB. So means RB, if you observe the voltage divided network bias, so that RB is nothing but parallel combination of R1 and R2. So hence first identify this RB, that is a parallel combination of R1 and R2. Then again you can observe this parallel combination of this RB value with HIE value, means input impedance value. So here, based on that RB, you can identify this 40 kilo ohms is parallel with 4.7 kilo ohms. That parallel combination gives that RB value. Then you can substitute here again this parallel with HIE. So hence that Zi gives that, means you can substitute this RB value 4.2 kilo ohms is parallel with 3.2 kilo ohms, means 4.2 into 10 power 3 into 3.2 into 10 power 3 divided by 4.2 into 10 power 3 plus 3.2 into 10 power 3. When solve this ratio, it gives that Zi value is 1.82 kilo ohms. Now we need to find out the output impedance for CE amplifier. We know that Z0 is parallel, that is equal to RC value. So directly the RC value is 4 kilo ohms. And similarly, we need to find out the voltage gain from the small signal model. So hence the voltage gain is represented as minus HFE times of RC by HIE. So HFE is 100, so hence minus 100 into RC value is 4 kilo ohms, 4 into 10 power 3 divided by HIE value is 3.2 kilo ohms. Then you can solve this one. It gives the voltage gain is minus 125. There, this negative sign indicates a 180 degrees phase shift with respect to the input signal. Now, similar to that, we need to find out the current gain of C amplifier, that is represented as minus HFE times of RB by RB plus HI. If you want to these relations, you can refer that SE amplifier analysis using small signal model. So from that session, I taken this mathematical formula CO directly. So hence this is minus HFE times of RB by RB plus HI. Just you can substitute this HFE value 100 into RB value is 4.2 kilo ohms divided by RB value is 4.2 kilo ohms plus HIE value is 3.2 kilo ohms. Then it gives that the current gain is minus 56.76. Now another problem. For the emitter followers shown in below figure, the circuit parameters are the RS is a 500 ohms, R1, R2 that is equal to 50 kilo ohms, load resistance is a 2 kilo ohms, HFE is 100 and HI is a 1.1 kilo ohms. Determine the input resistance, output resistance, current gain and voltage gain. So the given circuit is a common emitter follower, means a common collector circuit configuration. So we know that in a common collector circuit, the output is taken from the emitter and the circuit is called as emitter follower circuit. Then from this analysis, now we need to find out how much input resistance and output resistance and current gain and voltage gains are related to this problem. To understand this one, first you refer this a common collector amplifier using the low frequency model analysis video session. Then you take that mathematical relations to solve this problem. So here I directly taken that those mathematical relations to this problem. So first I am going to calculate this input impedance or input resistance Ri. It is represented as for a common collector amplifier or emitter follower circuit. That input resistance is defined as HIE plus 1 plus HFE times of RL. So here the HIE value is 1.1 kilo ohms plus 1 plus HFE is 100 and the load resistance is 2 kilo ohms. And to solve this one, it gives that input resistance is 203.1 kilo ohm. Now similar to that, so we have the voltage divided network, hence we need to find out the total input impedance. The total input impedance is represented as Ri dash. That is a parallel combination of input resistance as well as R1 and R2. Now we can substitute all these values to observe this total input impedance, that is 22.26 kilo ohms. Now calculate output impedance, that is R0 is equal to HIE plus R dash S by 1 plus HFE. First we need to calculate this R dash S. So where R dash S is the parallel combination with RS and R1 and R2. So first calculate that R dash S by substitute this RS values around R2. Then gives that RS dash is 490 ohms. Then you can substitute this RS dash here, HIE value and RS dash and 1 plus HFE. Then it gives the R0 value. That R0 value is 15.74, means HIE value is 1.1 kilo ohms plus R dash S is we observe that 490 plus 1 plus HFE value is 100. To simplify this ratio, it gives that output resistance is 15.74 ohms. Now we need to calculate total output impedance, that is R0 dash is the parallel combination with R0 and RL. So R0 we observe that 15.74, that is parallel combination with the load resistance, that is 2 kilo ohms, 2 into 10 power 3, hence 15.74 into 2 into 10 power 3 by 15.74 plus 2 into 10 power 3, that is equal to RO dash is 15.62 ohms. Now calculate the current gain for this common emitter follower circuit or emitter follower circuit, common collector amplifier or emitter follower circuit. So that is A is equal to 1 plus HFE, means 1 plus 100, that is nothing but a 1R1. This is current gain. Now similar to that, identify this voltage gain for emitter follower circuit. So that is 1 minus HIE by RA. So 1 minus HIE value is 1.1 into 10 power 3 by RA value is 203.1 into 10 power 3. Then it gives that the voltage gain is 0.9946. Now we will discuss the part B questions, that is solve theoretical questions. So solve the stability factor for voltage divided by circuit using transistor with a circuit. So for this question, first you draw the amplifier with voltage, means is common emitter configuration with a voltage divided by circuit. Then identify the stability factor. So for that case, you can find out the how much base current the flows. Like that, you can do. If you want, you can refer this a voltage divided by circuit video session. Then the next one, explain the two important factors to be considered while designing the biasing circuit, which are responsible for shifting the operating point. So here we need to identify the temperature dependent considerations, as well as proper DC voltage sources and proper biasing resistances are required to maintain that Q point. Then construct the collector to base bias using the transistor and derive the expression for stability factor. So for this case, first you draw the circuit for collector to base bias transistor, means like this. So it is biased with VCC, RC, and it is connected to collector. And collector to base bias means a resistance is biased from collector to base. This is RP, and here it follows the IB current. So here means this is IB plus IC current is the flows. Then emitter is a grounded, collector, base. Here we need to apply B. So draw the circuit, then derive the expressions for IB and IC and VCE. Then derive the stability factor S. So if you want, you can refer this collector to base bias session to identify the stability factor. So like that, derive the stability factor for fixed bias circuit using the transistor with a circuit type. So for this case, first you draw the circuit for fixed bias. So means this is VCC, RC, it is connected to collector, and this is the emitter. So for this fixed bias, the base resistance is directly connected from the DC source. It allows the base current. Here it allows the collector current, and this is the emitter current. And here we need to apply Vn. And this potential drop is VBE. So draw this one. Then identify the collector current equation, base current equation, and the Vce parameter here. Then identify the stability factor. Demonstrate the bias compensation techniques in transistor using thermistor and transistor. So actually, due to the temperature, we know that for every 10 degrees centigrade, the reverse saturation current becomes double. If reverse saturation current becomes double, means it affects the output current. So that is the reason. If IC is affected, the operating point is also affected. To compensate this one, we have the method, that is thermistor method and the transistor method. So for this case, first you draw the circuit diagram by the thermistor and again transistor. Then you can explain how it will be compensate the rate of change of collector current with respect to the temperature parameters. If you want, we can refer the bias compensation methods video session. Then solve the expressions for current gain, voltage gain, input impedance, and output impedance for common emitter amplifier using the low frequency model. So for this case, first you draw the small signal model for common emitter amplifier. Then by using that model, then you can derive the expressions for like this current gain, voltage gain, input impedance, and output impedance. So then for this case, you can refer that CE amplifier analysis using the low frequency model analysis session or video session. And similar to that, show the circuit diagram of CC amplifier using hybrid parameters and derive the expressions for current gain, voltage gain, input impedance, and output impedance. So for this case, first you draw this small signal model for common collector amplifier using the low frequency model. Then apply the KVL analysis at the input side and output side to identify the input impedance, voltage gain, and current gain, and output impedances. So for this case, you refer that CC amplifier using low frequency model analysis video session. Then illustrate the approximate model for CE model amplifier. So in this case, the approximate model means, and generally based on the low frequency model, we have the four H parameters: HI, HR, HF, and HO. So generally, HR is always approximately equal to, means less than 1. So hence we neglected this reverse voltage gain, and HO means that is output admittance. So we have this, means here for this case HO times of ZL should be less than or equal to 0.1. Then we go for approximated model of configuration. So for this case, first identify these two parameters. Then, if for this approximate model you neglect this output impedance and the reverse voltage gain, then draw the equivalent circuit for this common emitter amplifier using the approximate model small signal analysis. Then identify the current gain as well as the voltage gain and input impedance and output impedance. So demonstrate the next one. The demonstrate the CE amplifier with emitter resistance and derive the expressions for AI, AV, RA, and R0 using the hybrid model. So for this case, means CE amplifier with emitter resistance. So in the previous question, we are not observed the emitter is directly connected to ground. For this case, you should draw the SE amplifier with emitter resistance. Then you can draw the equivalent model of small signal model. Then identify the mathematical expressions like current gain, voltage gain, input impedance, and output impedance. So for this case, you refer this CE amplifier with emitter resistance using the low frequency model analysis video session. Now similar to that, solve the expressions for current gain AAS with respect to, means where S means we need to consider the source resistance as well as voltage gain with respect to source resistance and power gain for common collector amplifier using the low frequency model. So for this case, first you draw the common collector amplifier using the small signal model analysis. Then apply the KV analysis to identify this current gain with respect to source, voltage gain with respect to source as well as the power gain. So for this case, you refer this common collector amplifier using low frequency model video session. So up to this point in this session, we observed that part A and part B questions from the module 3, that is transistor biasing and stabilization. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.